Okay, welcome back. So in many ways, the last section was far too abstract for it to actually be useful in any sort of application. The real reason why we define these transforms is to gain, in the discrete setting, is to gain approximate solutions. So what I'm calling here is now truncated, the truncated power transform. We want to think about this word truncated as basically saying it's any mathematical process that's traditionally infinite. We're going to stop it at a finite number, okay? And if it's infinite and it converges, then if you stop it at a very high finite number, then you're very close to whatever it would have converged to, right? That's kind of the definition of convergence, is you get infinitely close to something. And so if we truncate any sort of mathematical process that is truly convergent at a very large number, then we have something that very closely approximates what it would have converged to. And that's the idea of approximation via truncation. And we're going to truncate our power transform in the sense that, what do I mean by truncate the power transform? Work with n by n matrices and dimension n vector spaces. Because a lot of things get a lot easier when we just decide to stop at some point. And I probably shouldn't say n by n matrices and n vector spaces, because we're going to be double indexing that. It's k plus 1 by k plus 1 matrices and k plus 1 dimensional vector spaces. So we just choose a big K and we say, for that very large K, I have a matrix which almost represents my ODE. And then I end up with a vector space which is k plus 1 dimensions large, and that ends up with a kth degree polynomial. Well, what do we know about the polynomials is that if you take infinite degree polynomials with like converging coefficients, that is the space of analytic functions. So we're just basically saying, what is the kth degree polynomial, which is really in many ways the first k plus 1 Taylor series coefficients of our solution. That's what we're looking for here. So that's how we gain approximate solutions, by truncating. We say, okay, our computers can only handle finitely large matrices. In some ways, our brains can only handle finitely large matrices. Let's just do it, truncate it, and get something that's close to the actual solution. So to do that, I'm going to start with this thing I call capital P sub deg k. So it's polynomials of degree k. That's what I'm going to call this, centered at t0. That's what I mean by this space. This is a space of polynomials of degree k, and in particular, every element of this space, p of t, is a polynomial centered at t0. So I have some analytic coefficients here, but I only have to jump all the way up to degree k on my series. I don't have to go any higher than k. And then what I go from there is I call something the k truncated power transform, and understandably, don't get confused that it's k truncated, even though our space is dimension k plus 1. You just have to make a choice, okay? So there's k plus 1 entries in our k truncated power transform, and we're going to define it as taking an analytic function. I'm putting a sub k by my power transform. I'm going to take an analytic function, which has its nice Taylor series representation, and I'm going to consider this as a vector, but I'm just going to stop it. So think about it as the first k plus 1 coefficients of Taylor series for f. Okay, so I'm going to grab the first k plus 1 coefficients of the Taylor series, I'm going to put them in a vector, and it's really nice now I'm in a finite dimensional vector space. So I can use every tool imaginable from linear algebra. When we're sitting in the infinite dimensional vector spaces, I have to restrict the tools I'm allowed to use because, I don't really know if something's converged in an infinite sense. So I really get lucky when I just say, fine, I'm going to stop it at k. Now I'm truly in the linear algebra sense of a vector space. So now this is another fun thing about pseudo-inverses, is that this k truncated power transform has only a pseudo-inverse. So I can act the same, technically it's like the same power transform, but I should probably put a sub k on it, so maybe I'll put a sub k on it now. But I can act the same inverse power transform, but the only thing is that it's only going to reconstruct me in this space of analytic functions. It's only going to reconstruct me up to the kth entry. And so I just have to be content saying, okay, I can send myself into this finite dimensional space, but if I ever try to send myself back, I get stuck at k. This is what we call a projection, and I think you talked about projections in linear algebra as well. So basically I'm projecting onto the first k plus 1 dimensions of my space of analytic functions. And because projections aren't invertible, we have to settle for the pseudo-inverse. But that's just something to keep in mind. It's just reconstructing some vector of coefficients as polynomials. Right, this is just a polynomial of degree k. Okay, Now, the nice thing about this is that the next couple examples, my derivative is literally the same matrix I had before. It's just not infinitely large. I've decided to stop it at a k plus 1 by k plus 1 matrix, and it's just what it is when I truncate that matrix. Similarly, if I decide to multiply by the function g of t, if I decide to multiply that as a matrix, it just stops. And it makes a lot of sense because this function now is exactly the k plus 1 dimensional approximation to my original function g of t. So this makes perfect sense. Within the space of k degree polynomials, this is the function which is closest to the original analytic function that I started with. So we just chop that matrix off as well, and so we're literally just dealing with like this k plus 1 dimensional space. So now I have the same version of the previous proposition, but it settles for k truncated power transforms of my ODEs. So I take an ODE, linear, still has to be linear. I take a linear ODE in one dimension and I act the k truncated power transform on it, and the operators, the m, multiplication by this lowercase mj, and then j derivatives exactly translate as before, but I've added a little subscript k here because they're not truly the same operators, right? This matrix does not fully encompass whatever that m sub j is, unless it's only a k degree polynomial. If it's anything more complicated than that, this is an approximation to multiplication by that function. This derivative is an approximation of the derivative on y, and that's why I've put k's in front of it, and similarly with lk. And then what I get is it doesn't look like it right now, but this is a matrix vector equation. This is a matrix vector equation in k plus 1 dimensions. In particular, the matrix vector equation is L sub k of v, I'll even call it x actually, L sub k of x, because then this looks like the matrix equations that we're used to, equals b. Okay, where L is that, right? If you decided to actually compute this out, you would get a matrix. So L is that, x is p sub k of y. We don't know what it is yet, we're gonna solve for it. And b is p sub k of f. And we also don't know what that is. Well, we do know what it is, but we haven't defined f yet. And so we solve it. Let's say hence solved by inverting L. You just have that x is LK inverse on b. That's all we have to do to solve this equation, which, you know, at one point in time was a differential equation. We're saying, hey, I don't want to solve differential equations, I want to solve linear algebra equations. And so all we do is we solve this linear algebra equation as we always would, but we have to be careful about a few things because, you know, keep in mind, not all matrices are invertible. And in fact, most of the matrices we're working with will not be invertible. Most LK will not be invertible. And because of that, that's why we are really emphasizing this idea of the pseudo-inverse. The pseudo-inverse is the next best thing to an invertible matrix. And so we have to get used to a pseudo-inverse, and then it turns out we can still often solve this equation with a pseudo-inverse. It's just that the solution's not unique. Okay, once you have a pseudo-inverse, you lose uniqueness on your solution. So we will lose uniqueness of solution. That's actually a good thing. You might not think that it's a good thing. It's a good thing because what is the homogeneous solution to an inhomogeneous ODE? Well, it has constants out front. It has C1 and C2 for a second order ODE. You have a C1 and a C2 out front. That means that your solution is not unique. So actually, to find any sort of homogeneous solution to the ODE, you don't want uniqueness of solutions. You want something non-unique because we have those free parameters C1 and C2 in the ODEs. So let's scroll down. There's our approximate homogeneous solution. And what you see from before is that what I've done is I've taken this idea of the identity minus the pseudo-inverse on L. In fact, this reconstructs the null space. And I'm going to act that, I'm going to scroll down a little bit farther. I'm going to act that on an arbitrary vector v. Okay, so I'm just going to choose some arbitrary vector and look at the image of the identity matrix minus LK inverse LK. I'm going to look at the image of that. That's going to give me the null space of L. And it's actually an exercise that you're going to show that it's a null. It gives me the null space of L. And then I have this funky thing, L pseudo inverse on U sub n. And what is U sub n? U sub n is a matrix, so n being the degree, or the order. N is the order of my ODE. There's my ODE, there's my order. U sub n directly depends on the order of my ODE. And it's an arbitrary vector whose last n entries are undetermined. So we haven't determined the last n entries. The first n entries are all 0. I guess k plus 1 minus n entries are all 0. So the first k plus 1 minus entries are all 0. The last n are non-zero, but they're arbitrary. And this is why am I acting this on arbitrary, right? Why are v as a vector, make sure it's boldface, and u n as a vector arbitrary. It's because the homogeneous solution, y sub h, needs arbitrary parameters in it. These are my C1, C2, etc. for higher orders. When I construct the homogeneous, you've done this already when you're doing homogeneous solutions to kind of these classical differential equations that you found out how to solve. You were putting C1 and C2 in your answers, and so these have to show up somehow if we're approximating it, and this is how they show up. They show up right here by choosing arbitrary v and arbitrary un. Okay, what's not arbitrary is a particular solution. You'll notice that all I need to do for my particular solution is act the pseudo-inverse on my resulting vector and then send myself back into the space of polynomials. I'm going to get an approximate particular solution. Maybe I should have put a k right there, y sub kp. So I'm going to recover an approximate particular solution by just inverting my matrix as best I can and sending myself into the space of polynomials. And so there's nothing arbitrary about that term. Finally, the general solution is just the sum of the two of them. Now that's really fancy notation for saying I've just taken the sum of the last two. Okay, so I'm calling this y sub k because it's only an approximate solution to the kth degree polynomial. This constructs approx solution up to k degree polynomial. So that's what I recover here, and that's why it's an approximate solution. But I have a formula that will necessarily do it for me. That's the nice thing about this section, is that these formulas work, and they work using the tools of linear algebra, which we 100% have perfect knowledge of. Like, the computers can invert matrices day in and day out. They're never going to fail to give us a pseudo-inverse of a matrix. It might just take a long time. Okay. By approximate solutions, I mean that as k tends to infinity, we do actually recover the true solutions. This is something really nice to know, is that, in fact, the limits as I take k to infinity of each of these solutions will give me the solution to the ODE. Okay, so let's actually do this, the example that comes up, because otherwise, you're all going to be like scared about how to do this, because maybe it's not so clear about how we do this in practice. So here's a nice example. It says find a polynomial of degree 5. I want to interpret that as k is 5. Okay, so k equals 5, centered at x naught equals 1, which approximates the general solution to the ODE, and it's the following. X squared y double prime minus 2xy prime plus 2y equals x. This is an equation of Cauchy-Euler type, so you do already know how to solve it, but I want to see that you know how to solve it or approximate it using the power series, truncated power transform. And if we're going to center it at x0 equals 1, we have to do something special, right? Because each of these coefficients needs to be expressed as a Taylor series centered around x equals 1. Express as Taylor series around x naught equals 1. I'm not allowed to work with them as they are if I'm centering the ODE somewhere other than 0, because the way they're written, they're centered at 0. So let's just do that really quick. X squared as a Taylor series centered at 1. I can either calculate derivatives and evaluate 1 and then multiply by the Taylor series terms, or I can do the following, which is my favorite way of doing this, is we rewrite it as a function centered at 1. And then we have to add 1 to account for that, and then square it. And then we FOIL this out and we recover x minus 1 squared plus 2x minus 1 plus 1, if I FOIL that all the way out. And there's your Taylor series centered at 1. Oh, okay. Moving on to negative 2x. we can play the same song and dance. This is x minus 1 plus 1, which if I separate it out is 2x minus 1 minus 2. And then finally, 2 is equal to itself in Taylor series. So that's just something we have to be careful about if we're centering ourselves somewhere other than maybe how the ODE has been represented. Okay, because these coefficients, 1, 2, and 1 in the first case, -2 and -2 in the second case, and 2 in the third case, these are our entries in each M sub whatever matrix, right? We have these matrices that contain entries, and the entries are the Taylor series coefficients. We can't forget that. So the important thing to do is to represent things in terms of the Taylor series coefficients, as well as remembering what the derivative matrix looks like. So let's scroll down now. And I mentioned that here, right? So I rewrite it, everything. Oh, and the function on the right-hand side as well, right? That x is just x minus 1 plus 1 as a Taylor series centered at 1. So here we see now, this is my ODE represented in the form where every function is a Taylor series centered at that specific point. So that's my function. It's the Taylor series centered at each point. And now it becomes much more clear how I represent this in terms of matrices. So let's look at each term here. So x squared, or x minus 1 squared, is the matrix which corresponds to multiplying by x minus 1, and I've squared that matrix. 2 times x minus 1 is 2 times the matrix which corresponds to multiplying by x minus 1. I have a random 2 over here that's not supposed to be here. And then finally a 1 just corresponds to the identity. You could represent that as the matrix which corresponds to multiplying by x minus 1 to the 0 power if you want to. That's totally fine. But it's much easier to just think about the 1 as the identity matrix. So this 1 is the identity matrix. And then what is two derivatives? Two derivatives we represent as the derivative matrix squared. Similarly, I represent multiplication by -2 is still multiplication by -2. I can say multiplication by x minus 1 is precisely multiplication by x minus 1. And once again, multiplication by 1 is the identity. A derivative is the derivative matrix. And then 2 multiplications by the identity is just 2. And so this is kind of the way that we have to reinterpret these ODE problems in terms of matrices. We just represent each multiplication as the multiplication matrix, and we represent each derivative as the derivative matrix. And we just have to be clever about calculating that out. So if I actually go through that process, there's my matrices. And it's really interesting because at the end of the day, all that happens is I literally calculate all of these matrices out, go through the matrix multiplication. This is why Wolfram is very useful. Go through the matrix multiplication, add them together, and we end up with a matrix which is just a matrix. So we can 100% represent my matrix right here, which completely represents my differential equation up to I guess 5th degree polynomials. This is the differential equation in 5th degree polynomials, which is kind of a cool thing to think about. Is that the differential equation feels nothing like a matrix until it does, and then it's literally only a matrix. So we can gain L as a matrix out, and we can compute the pseudo-inverse. So on Wolfram, you just type in pseudo-inverse. That's a very easy code to memorize, pseudo-inverse, and you just plug it in and you get a pseudo-inverse of L. And then we also define maybe our x, which will help us reconstruct our polynomial at the end of the day. And then finally, I have my whole idea of trying to find the homogeneous solution, where you can start with an arbitrary v, and I would advise that when you're doing this early on, you do start with an arbitrary v, so just c1, c2, c3, c4, c5, c6, and same with u. You'll recall, since this is second order, I need 0, 0, 0, and so on. That 4, by the way, in the superscript is a footnote, and it's explaining why. I can just worry about a 0 for you right away. But anyway, if I calculate then the null space, right? So the identity minus the pseudo-inverse on L, and I act that on V, and then I take the pseudo-inverse on U, what results is C1x plus C2x squared. And in fact, that is a homogeneous solution. It's not even approximate in this case. So, right, we just saw that this constructed C1x plus C2x squared let's take two derivatives of that and see what we get. So if I take two derivatives, I get just 2c2. And if I plug 2c2 into there, I get, I guess, 2x squared c2. And then I get minus 2x, one derivative, yh prime, one derivative is c1 plus 2c2. So there I get c2c2x. c1 plus 2c2x. Finally, if I plug yn, I get 2 c1x plus c2x squared. And what we would end up seeing is negative 4 c2x squared plus 4 c2x squared. So we get 0 in c2. And in c1, we have negative 2x c1 and positive 2x c1. So we get 0 in c1 as well. And all of a sudden you see we truly have a homogeneous solution. And we got there using matrices, which is absolutely crazy. So that's really something cool to think about here. So that constructs our homogeneous. And then the approximate particular solution, because the right-hand side, let's look at the right-hand side of my original ODE. So if I need a particular solution, I'm considering the right-hand side. If I write that as a Taylor series, the first coefficient is a 1, the second coefficient is a 1, and the rest of the coefficients are all zeros. So as a vector, the first coefficient is a 1, the second is a 1, and the rest are all zeros. And if I act my pseudo-inverse on that and then reconstruct a polynomial, I get the following, which is really, really ugly. We're starting to notice a pattern here about the 1/6, but the rest of it gets really ugly. That's why we have a computer do it for us. But what we get then below is we add them together, and we have ourselves an approximate general solution, right? There's a C1 and a C2 on the first three terms there, and then the bottom terms are only part of the particular solution. And from this point, since we have two parameters, two free parameters, it's straightforward that we can approximate IVPs or BVPs, right? Because we have two free parameters, we should be able to approximate any IVP or any BVP. And so let's look at that. This is the same ODE. It's the same ODE, but now I've added an initial condition. And in fact, we want to center our solutions at the initial conditions for very straightforward reasons. But so now that we've been given an IVP, we can just plug them in and solve for C1 and C2. We just gain a system of equations in C1 and C2. Two equations, two unknowns. You can solve this by any means you want to, but we get that C1 is 1/2 and C2 is 1/3. And so plugging those numbers in, we end up with the following Taylor series. So the Taylor series looks like it probably has exact coefficients up to the first three terms because those are pretty well behaved. And then these are probably really close to like the exact terms. So this is probably something like 1/80. In reality, this is probably something like 1/24. In reality, this is probably something like 1/8 in reality, maybe. So if we then by Cauchy-Euler type, we can actually find a real solution to this IVP, and then we plot them against each other. Or actually, we look at the power series coefficients first, and we'll notice that, yeah, the first two terms perfectly line up, the second two terms perfectly line up, the third two perfectly line up, and then, after that point, they differ a little bit. But if we plot them against each other, the approximate solution is the one in red there, and the true solution is the one in black. And especially, we centered our answer at 1. Look at how closely those behave around 1, but even in a region pretty far away from 1, they really behave very close to one another. And as you took k higher and higher and pushed it to infinity, you would get exactly the right solution. So that's how you work with these in practice. I know it's really tricky. We're gonna have to get good coding, happy coding, practice with Wolfram, but you'll get there. And this is probably the most useful thing you can learn this semester, because this is how we do any sort of numerical analysis in the real world. So that's all I have for you today. Thanks for sticking with me. I'll see you in class. Bye.